Hey, good evening, everyone. It's super excited to again start this session on multi-arm bandits. Um, so this is me, Setu Choksi. I'm the Microsoft MVP, and over this session and the next few sessions, we are going to look at exploring multi-arm bandits and kind of build all the way into contextual bandits. And towards the end, if time permits, over the next couple of weeks, we will also start to explore contextual bandits and more specifically one of those Azure options on personalizers. But the next 2-3 sessions, depending on what feedbacks do I get, we might end up going deeper into some of the key algorithms, understanding some of the key concepts in there before we jump out and do other things. So some of the sessions that we have, will cover the following things. So today, the idea is that we will look at the fundamentals. We will start off with our multi-arm bandits, and understand how they work, understand what we can do with them, and at least get a basic concept with Epsilon-greedy. Again, depends on how the time goes. We might decide to kind of spend some more time, but of course next time we want to spend some time more on the algorithms itself, which would deal with flavors of UCB. Again, if you don't understand those words, it's okay, you will understand it. Thompson sampling, Bessa, and there are a lot more. In the subsequent weeks, I just wanted to kind of keep it open-ended and see, do you want to kind of go deeper into more algorithms, or do you want to kind of spend there? So I'll just pause for a minute to see what you guys want, and depending on your interest, I'll kind of tweak the presentations in there. If you have any suggestions of what you guys want, should we spend more time on applications or more time of algorithms, you can just write it in the comments, and would be happy to kind of explore it further. So there's one question. I'm curious about the algorithms and how they generalize beyond the discrete settings. The applications, so it depends on how you kind of set it up, and over this course, we'll kind of go into some of the specifics of what assumptions you make, what simplifications you make, to kind of get there. And there are a lot of ways to kind of think about these applications itself. So for example, I've seen examples of this being used as a intelligent A/B testing, something that we'll cover as well. Some of these guys have gone and done dynamic pricing. Some of these guys have built promotion engines on top. So it kind of all varies with what sort of topics that what sort of problems that you're working on, and all of these kind of work out with these options. There are also, in the machine learning world, I assume, most of you are familiar with the machine learning concept like ensembles. There are new state-of-the-art algorithms which talk about, combining multiple of these algorithms into an ensemble, and then, there's another logic that sits on it, which then starts to pick, which is a better model to go work with. So those are some of the things that you can work out with. All right, let's proceed ahead. So one of the motivations, and I always would love to start with some easy examples that people could relate to, and everybody knows about these things on Netflix. Netflix is one of the key things that everybody is aware of globally. Now they have launched. And some examples that I really came across, and I have this links and I will post it in the comments as well, is how they do artwork personalizations, and they also have done something around Netflix recommendations as well, how they use this. So now instead of working out and saying that there's going to be a same artwork for everyone, they have kind of created a variety of artworks, and each one kind of is driving a theme within for that particular episodes, series, or the movies itself. And they are kind of using this to kind of elicit feedback, so that somebody who's interested in that will kind of go and watch it itself. So something that they end up doing as well. And if you look at it, right, in terms of how the context of this could be used, which is the idea around contextual bandits, is that, hey, if somebody is watching a lot of romantic movies, then having a poster which has Matt Damon and Minnie Driver is kind of a useful, again, kind of to showcase the person that, hey, these are romantic movies. But on the same concept, right, because the movie also have Robin Williams and somebody who's watching a lot of comedy movies, so it would be better that they end up recommending Robin Williams for the poster, because he's a well-known comedian, and people might want to kind of watch that movie for some of these things. So again, these kind of artworks are kind of based on context of what the user has done on the Netflix platform itself, and gives you a good idea associated with these. The next one that comes in is, again, you could again, kind of build this up in saying that, all right, if somebody has watched a lot of Uma Thurman movies, then, maybe Pulp Fiction shows up with a poster of Uma. Or alternatively is, I could do the same poster with John Travolta based on some of the commonalities that you have. Now again, if somebody who has done recommendations, you will quickly notice some of these things is like, hey, these could be user vectors that I could kind of leverage out and combine it with the movie vectors as well, and then figure out what recommendations we could do as well. So instead of going down the recommendation path, multi-arm bandits give a faster learning times, something that you can leverage as well. So in this example, what they kind of wrote up in the blog is the time sensitivity is of key. Because let's say the Game of Thrones gets released, again, this is not with Netflix but with HBO. You might want to kind of recommend something similar, right? And people's interest in the content also kind of evolves based on what the user or what the viewer is kind of interested in. So it's very, very dynamic in that sense. And right, if you wait for sufficient feedback to drive the recommendation algorithms, they are not going to respond very quickly. Yeah, of course, there are some of these algorithms that you can kind of work out, but then again, you're kind of limited to what we have. And for Netflix, the other thing is the content, the non-stationary idea of it. The content is varying by country. The catalog is always evolving. You have new movies come in. You have some of the movies, no longer on the Netflix platform. And also the user base is stationary, right? Again, with some of these things on HBO, if you notice that, people specifically subscribe to HBO when the Game of Thrones comes in, and desubscribe it, once those series are over. And you would see some patterns with that as well, now that Netflix is kind of doing some of their own series, and something that to keep in mind. Now again, having said that, it's not like the multi-arm bandits or contextual bandits don't need a lot of data. They do need a lot of data, but then this can turn into an online learning kind of algorithm where, based on certain key metrics, I can work with the users fairly quickly and build a model, introduce new artwork without having to go about and retraining the model itself. The other advantages that you can get is if you have some pre-known features that you would have from the users as well, you can pre-train some of these multi-arm bandits models, right? We have these things of priors. Again, don't worry about the terms. We will kind of get into the details, but that's something that you can, start off with your basic assumptions of what you think the users will like, and that can be a starting point for the algorithms to go out and pick it up. So contextual bandits or multi-arm bandits provide a great starting point, which can be either augmented with your recommendation systems or can be used in itself as an online learning algorithm itself. I'll just take a pause here to see if there are any questions on either of the platforms, specifically on YouTube or Twitch. Again, give me a moment. I'll just kind of check on if there are any that are popping up. All right. Looks like there are no other questions. Let's move on. Now, again, most of these ideas, you would have said, hey, why can't I learn a machine learning algorithm? Or let's say I have a very powerful recommendation algorithm. Why don't I do an A/B testing? And let's say you do go down the path of doing A/B testing, right? Your first step is you're going to collect a lot of data. You're going to build a model, and you'll spend some time putting that model into production. Maybe you develop more than one model that's sitting in there. Then you will start your A/B testing itself, and your next step is going to be where you will roll out. Let's say your model B was successful, you will roll that model B. Now you can see that you took some time to kind of go from collecting the data all the way up to rolling out a model B. Right? This cannot happen within a few days, unless of course you have everything sorted out. But most likely that usually doesn't happen. And what happens in this scenario is specifically all the way from collecting to the point where you are doing this A/B testing. I would call this as regret, because a lot of features, attributes that you are kind of doing for your consumers really doesn't work out that well, right? So let's say you are rolling out a new experience, right? In case of Netflix, they were rolling out these artwork selection. The users won't see that effect come in till we go on and deploy those models, right? So people are not going to see that benefits. In other scenarios is, there were a group of people who really liked the model A as compared to model B, right? And now when you roll out model B, these guys are going to have to compromise with the option that you have rolled out. So instead of doing your traditional A/B testing, having ideas of contextual bandits or multi-arm bandits allow you to kind of serve both A and B and other models as well as you go along and deploy some of these things. So that's a very good way of using using multi-arm bandits over A/B testing as well. Now let's look at what are these algorithms, right? We have kind of talked about the motivation of why you should be looking at multi-arm bandits, and of course there will be some other ideas that you could pick up from these algorithm itself. So let's kind of build some motivation and how would we deploy these algorithms in real time on that. So your traditional programming, the way it works is, or your machine learning algorithms is, you will get an input. You will capture this through various means. You will have your algorithms that you are going to train your input on, and then you are going to get some output, right? So this becomes your traditional programming or machine learning models itself. In machine learning, you could get some feedback from your output. Let's say you put that model into production, you could tweak that inputs or you could tweak that algorithm in there. But that's how it keeps on going, and there is no other inputs that you can use to kind of train your algorithms or provide more feedback in there. In case of reinforcement algorithms, and this is where I'll kind of introduce that term, you have this agent. Agent is another way of calling an algorithms or policies itself. That's just what we call it. What your agent is going to do is going to observe the state, right? It could be contextual, or it could just be a time step t. It's going to observe that, and it's going to pick an action from the choices it has. The action will act on that world. Let's say you are doing some movie recommendations, you are doing some sort of motivation for people to click on that series in the case of Netflix, and depending on that, you will give the reward, right? So the reward could be that, hey, somebody clicked on it and I could give a reward of 1. If somebody didn't click on it, I would, after a point in time, I would kind of give it a 0. But when you kind of give that action, the world changes, right? So the states of the users have changed itself, and then you have a new observation state that again the agent can observe and make decisions on which action to take. So this whole action reward scenario and the state becomes your concepts on reinforcement learning itself. All right, and the states, these could, there is a very, very good chance that you cannot observe all the states possible. And for simplification, whether it's contextual bandits or your multi-arm bandits itself, you don't want to observe all the states. And later on I'll kind of give you that simplification of why that shouldn't be the case itself. But other than that, you can kind of keep working off this actions, and these actions could be different offers that you are showing to your consumers, different artwork that you are showing to the consumers, or different choices the users can make, which will kind of give the reward back to the agent so that it can learn itself. So you would have seen that in more of a biological terms, right? And the classical conditioning or the Pavlovian conditioning is how people have traditionally trained their pets as well, right? So you would have let's say a dog. Now you are kind of training the dog to kind of go fetch that ball, and if it does that action, it gets a reward, and the dog can then associate that with a good action that it has to take. And the trainer in this world is kind of giving the dog the candies or the bones or the treats to make sure that whatever action did the dog took, that is kind of helping the dog to kind of learn and associate it with the positive feelings as well. And again, in the biology or in your day-to-day interactions, that's how most of us have been groomed as well, right? If you do a good action, or you increase revenues for your companies, you benefit your companies, you are given with more monetary rewards, you are given with better promotions, higher ranks as well. And that's something that you associate with whatever you just did with the positive actions itself. And that's how you kind of build that reinforcement learning. So that's a very good idea to kind of think about of how reinforcement learning works. Again, I'll just take a pause for a couple of minutes to see if anybody has any questions, any comments that you would like to make or me to clarify so far. All right, let's move on. So now we have been talking about multi-arm bandit. All right, so there's a question that has come in here is what is the difference between reinforcement learning and learning from data set? All right, so in our traditional way of working through that, again, reinforcement learning can also learn from the data, but it's that reward part of that feedback loop that you are kind of giving it back to the agent, where it's now learning whether that action was good or bad, and whether it's going to pick it from not. In your traditional machine learning world, there's no feedback that's going back into the model itself unless you are kind of labeling that data as you go along. So there's no feedback loop that's telling the model it's like, hey, it was a good model or a bad model, but something that you might kind of go back to your model take your new data set that has come in and train it again. Again, there are algorithms that you can kind of use for online training or online learning as well, but that's completely dependent on the approaches that you end up doing. All right. Some of the other things, we have been talking about bandits, and I never introduced what was bandits, right? So, in your multi-arm, arms are basically the choices that you would give to the users. While rewards, if they are not delayed, it becomes a bandit problem. Means that within a matter of minutes or few hours, you will know what the reward is associated with that, right? And that's how you would kind of define a bandit problem itself. So your multi-arm, your arms are your choices, your bandits are rewards that are not delayed. Now, reinforcement learning, especially these days, people have come up with some new approaches where, they can start to play games, they can learn from the users, how to play chess or the game of Go itself. Over there, your rewards are delayed, right? You don't know whether the actions that you took are making you are going to help you win the game or not, and that's something that you have to keep in mind as you kind of go along, right? So if it's a reward that you can measure fairly quickly, then it becomes a bandit problem. So keep that in mind as you kind of think of different ways in which you could apply the bandit problem itself. Now, let's take this example a little bit further, right? So now let's say you are in a casino and you have a bank of slot machines from which you are going to pick, right? Now, again, we'll kind of keep our slot machine very simple. Either it gives you a reward or it doesn't give you anything. So either you get $0 or $1 itself, right? And you don't know what state each of the machine is, right? Is one closer to giving you a jackpot, or the other just gave a jackpot a few hours back, and there is no money that is associated with that, right? So given these three bandit machines, right, these are the three choices that you have to make, and you don't know which one is going to give you a better payoff, right? So how will you maximize your rewards over a period of time? So how will you pick machine A, B, C over a period of time, right? And the other way of kind of looking at it from the theory of machine learning is that you would want to kind of minimize the regret over a period of time, right? So regret is the money that you lost by playing that game. So similar ideas are available, are often used in multi-arm bandits as well, right? So this is a very typical concept that you will come across as we go into the code as well. Now, the other thing that you have to keep in mind is, when you pull an arm, right, you don't get to see, what would be the results when you pull the other arms as well, right? So this becomes your partial information of those things, right? So, between your three slot machines, you ended up picking slot machine 3. You pull an arm, you cannot play the other machine simultaneously, right? So you don't know that machine A or B would have given you different options, right? So that's something that you have, right? So you don't know what the other arms would have yielded in that scenario. Now we need to create some sort of a model, or in this case an approximation of how that world is working, so that we can figure out how do we maximize the reward over a period of time, right? So over here it's like, hey, which action have I chosen, and tell me something about that, so that I know that over a period of time I'm going to maximize my reward. One way in the slot machines, as you would think in the other ones, is what is my average wins over a period of time, right? So let's say I played slot machine A 10 times, B 10 times, C 10 times as well. That's one simple way to look at it, is like for every $10 that I spent, assuming each game is $1, how much money did I win back. And that could be a very, very simplistic way of kind of working through this. Of course, you can build complex models, but that's an idea of looking at rewards in itself. At some point, right, even though let's say you were on machine 3 and it gave you a jackpot, you don't know whether other two machines that you have, you would want to kind of explore them as well, right? Just to see, hey, are there any better strategies or better arms that are available based on the evolving nature of your state as well, right? So again, going back to your slot machine, you would want to know that, hey, if I have a slot machine C that just gave a jackpot, it's not going to give you a jackpot again, right? So probably at that point in time, you might want to go out and explore other machines as well. And that's something that you have to kind of keep in mind as you go along, right? So this is your exploration problem that you end up working with, right? So even though exploration is required, right, you would always want to kind of go back and go to your best arm, because that has given you better rewards over the past history that you have seen, right? So you will want to maximize your reward over that time period that you have, unless some new information that comes along which prompts you to change your arm that you end up picking, right? And this is where you have to kind of figure out your exploration and exploitation. Exploration is going to kind of get you more knowledge about other arms, other scenarios, while exploitation is you are going to maximize your rewards, right? So in the case of earlier scenarios where a certain artwork is suitable for certain users, now you will want to kind of exploit that to your maximum capability. But at the same time, you want to still keep on exploring other options so that you don't know whether that user taste has evolved, which will prompt you to kind of pick a different artwork that is more currently relevant at this point in time. Same goes on with the, let's say you're doing a news article for the users as well, right? If the world is talking about COVID or the dropping stock market, you might want to tune your rankings or recommend news based on the current scenarios of the world, and not just based on what the user likes. You could tune those headlines, but let's say recently the user has started to do that, you might want to kind of explore that and exploit that knowledge that you have gained. Now, we kind of talked about Bandit itself, but how do we solve the Bandit problem? Right. So, of course, we have to make some simplifications, and let's look at some of those. Right. So, for multi-arm bandits, we will make two very, very simple simplifications. Right. So for the first things, right, overall, when you kind of think about multi-arm bandits, your first thing would be coming is, let's go out and increase our user retentions, or let's go out and increase the stickiness of our website. Now those long-term rewards are typically very difficult to achieve. And we said that the bandit problem is something where the rewards are not delayed, right? So you cannot be waiting for months together to figure out whether your algorithm is taking the right action, your agent is taking the right action, or you will need something else as well. So now you could turn up with proxy short-term rewards instead of long-term rewards as well, right? So you could, if the dog does an action immediately, you would give him a small treat, and that's just showing that, hey, if you follow my commands, or if you follow my audio cues, you will get treats, and you will get more of them going up. So I have 3 examples on the left hand side, and I just wanted to kind of see if you guys had any ideas on there. The first one is you're trying to kind of motivate somebody to get weight loss. And again, you are trying to kind of build a multi-arm bandit associated with that. The next one that you would have is news recommendations. So how would you kind of look at news recommendations? And the third one is, let's say you are YouTube, right? And you want to kind of showcase, again, a similar type like what you had for Netflix, is artwork recommendations. So in all of these scenarios, you have long-term goals for each one, I just want to kind of see from the audience itself is what would be your substitute for short-term goals for making the multi-arm bandit work. Any ideas of thinking about what goals will you give, so that overall in the first example you get somebody to reduce weight, second one to have more retention on your website, same for your video site as well. So what would be short-term rewards that you would use to train your multi-arm bandit? Put your notes in the comments, and let's see if audiences have any ideas in there. All right, so there is one on Twitch. So for weight loss, if the agent chooses healthy food, give him a reward of 1. If he chooses unhealthy food, you give him a reward for 0. Same for doing workout and that. So that's a pretty good output from the user ceilings 1 to 3. So on YouTube, we could look at click times or watch times for that. That's also another one that you could use for. That's also another great response. Yeah, so I think you guys are starting to kind of get a flavor of how you can kind of do a proxy for a long-term rewards in days of short-term rewards as well. Same goes for views. Once you kind of do that recommendation, you could kind of use that as well, right? So that could be one thing that you could use of. Something which I had was exercise time. One of the users said on Twitch is like, hey, look at it in terms of doing workouts or not. That's another way of kind of thinking about it. For other ones, again, I come in from a very product oriented company, online company. So session duration is something that you could think of. Hey, you made a recommendations, how long did the user stuck onto your website? And the same goes for others as well, is on the view duration as well. It's like, hey, you did a recommendation based on the user features. How long did the users watched on your website as well? So those are the good ideas of how you can take a long-term problem and convert it into a multi-arm bandit problem and work through that process as well, right? The other simplification that you have to make is think of ways in which your previous action should not influence your current actions, right? So when somebody takes an action, right, in your previous cases, is somebody has clicked on your ad and you are getting the session duration, or somebody is trying to do a weight loss and trying to kind of lose weight, and he's doing that workout, your next action is not affected by the fact that the user picked another action itself, right? So the states are very, very important, and that's what's the simplification that we wanted to kind of make earlier, is you don't worry about different states of what the user is going to be, right? And you would say that, hey, for all practical purposes, the user is going to be that action is independent, and your long-term goal can be achieved by those short-term goals itself. So that's how you would kind of work through that. But that's a simplification that allows you to build your multi-arm bandit as we go along. All right. So again, let me pause off, just see if you guys have got these two concepts, because these are two powerful simplifications that we have to make before we go on. And let's see if there are any comments again on the websites. So there's a question on Twitch is how would you factor time into the reward? Would you try to distribute it or just use a Bernoulli approach, saying that when it's a fixed time? Um, so so there are different ways in which you can approach this, right? So for multi-arm bandits, some policies do allow you to look at reward versus times. But for most part, your time step has got nothing to do with what the current state of reward is in, right? And then you will see that time step t does come into the factor of how do you end up making choices as well. So that also factors in as well. The other approach is to look at context. So in that context, you could bring in different factors. Is that, hey, what were the previous states of the users that were in? Did he click on that ad? Did he take the action that you have? And that could be another context that you can certainly bring up. And a lot of the deep reinforcement learning algorithms or proximal policy algorithms do take that time step into account, and that reward is distributed over a period of time, right? So in the games of chess or in the games of Go, you don't know whether that reward is coming now, or most likely your reward is when your game has ended. So something that has to be taken that into account as you go along. There was another question from Dinesh early on Twitch, is how is action reward different from weight adjustment through backward propagation in deep learning? So that's again a great question, and a lot of the reinforcement learning algorithms, specifically that takes into account the neural networks ideas, do kind of take that approach in itself, right? But what happens in your backward propagation is you're trying to kind of pick again, based on how well the classification happened, you kind of try to propagate your weights. And if your network is deep, you might need a lot of iterations before you kind of get to again a better selection, right? And as you kind of look at through some of these algorithms as we go along, you would see that, hey, we would make a better choices based on the time itself, and that policy becomes more like a learning policy where immediately you get a reward, your state or your internal state of your policies is updated itself. So that's something that we keep in mind. While in case of deep learning, you would need a lot of feedback from your final results before you are able to train the weights of your neural network that's sitting in there. But of course, people have done this. Neural networks are used in some of the reinforcement learning algorithms, but over here, not in multi-arm bandits, right? Multi-arm bandits, we'll just focus on more of statistical approaches rather than deep learning approaches. But those are some of the neural networks are some of the ways in which reinforcement learning techniques have been used as well. Okay, so there's another one on possible states for a weight loss case, right? So all you're going to kind of look at it is your reward would be whether you have done a workout or not, and your final goal is your weight loss, right? Again, you could kind of go out and say that, hey, I'm going to look at the intensity of the exercises, or what exercises did the person do, probably link up with the diet as well, and that gets into different states of the users itself, of how that weight loss will kind of go in, right? So let's say somebody did an exercise for 40 minutes, he did cardio exercises, but then he went out and ate a lot of carbs, right? So that could be a context that is kind of giving in, telling you, hey, what did the users do before, and those are the states that are coming out in there as well, right? But for your multi-arm bandits, in most of these scenarios, we will ignore the context part of it, right? So we are going to ignore the state of the user. Instead, we'll just start to focus on the reward itself, is whatever action that I'm doing is affecting the reward or not. Akhil has another one. So the path to the current state does not affect the decisions made in that state. That is correct, and that is one of the fundamental assumptions of multi-arm bandit. Is your actions or your number of actions. Again, you can kind of change it. There's nothing mathematically preventing you from doing that, but your state is only dependent on the rewards that you are accumulating for that arm, and maybe the time step, but nothing more beyond that as well. Uh, so your actions, you may have 3 or 4 actions, or you may have more, but that doesn't really affect how you kind of go about making your choices. All right. So let's take a look at the agent design, right? So, like we said, right, we are going to ignore our context. We are just going to look at time t, and our agent essentially becomes a policy, right? That's another way that we'll kind of look at it. So at each time step t, you observe the state, and this state could be the rewards that we have obtained for each arm, and that is one way where we'll kind of stick in it, and then we'll pick an action. The policy can be deciding whether it needs to pick a best arm or it needs to explore. And again, the exploration is driven by the policy itself. So the policy is kind of making a decision whether it needs to do exploration or exploitation, and then the output of this is an action A, right? And this A could be you could have 2 choices, 3 choices, n choices, right? So that's an action that the user the agent is going to give out, right? Again, you will kind of give the feedback to the agent saying, okay, for this action A, you give a reward and you take the next time step t. So that's how you keep on going out and improving your agent as well. Now let's look at some of the basic algorithms that we have with us, right? So the first one that we took was the A/B testing algorithm, where we had the naive algorithm. So let's say I have 3 arms. So in your A/B testing, you are going to kind of run 100 trials for each of those arms, and then you will look at it as how much wins did I get, right? This could be my casino, this could be my prompt for the user to go out and do exercises, and every time he does an exercises, I give him a reward of +1, right? So my arm 1 won 2 times, my arm 2 won 21 times, my arm 3 won 17 times. So for the remaining M pools, so going forward from that state itself, I'm just going to pick my arm 2, right? This is our traditional A/B testing, right? This is how we have typically looked at A/B testing itself. Now this is not, again, very intelligent, right? So first we had a very distinct state of, first we did our exploration, and then we did exploitation, right? And there's no feedback that's going back in there, right? If you want to do a feedback, again, you are going to go back and do your exploration across all, where you are going to do 100 trials each, or you would start off with doing exploitation again. Let's say this time around arm 3 was doing better, right? So now your navy approach had your distinct things itself, but now you are going to do something different, right? When you are kind of going to be greedy, right? So now your arm 2 is going to be giving you better options. So now you are becoming greedy and say, all right, now I'm just going to focus on 2, and I'm not going to look at any other arms itself, right? That's your typical A/B testing approach. Now there's another approach in which you could say that, okay, I want to kind of balance out both my test A and test B. I know that I have my 3 arms, my arm 2 is doing better, and for some amount of time I want to kind of go back and spend time on doing this exploration itself, right? So what we do is we kind of pick a probability value, let's say 10%, and this could be anything depending on how much you want to kind of spend time on exploitation. versus exploration itself. So now what you're going to do is, given a set of arms, right? So in your previous scenario, you had 3 arms. Now you are going to select the arm with a probability of epsilon, right? So if your arm 2 was doing better, right? So 90% of the time in this scenario where my epsilon is 10, 90% of the time I'm going to pick an arm that's giving me more reward, while 10% of the time I'm going to pick an arm randomly out of those remaining 2 that I have, right? And I'll keep doing that, figuring out where my reward is. And here's where the user is telling the algorithm of what is a point when I am going to look at, or how much exploitation do I need to do, right? So 10% of the time I'm going to do exploration, remaining 90% of the time I'm going to do exploitation. And you could play around with these values as you feel comfortable with that. So as we kind of go through that, right, in my Epoch-greedy, I had 3 arms, each one had to do 100 trials. So my total N was 300. My M was, let's say, 1000. So for remaining one of them, I'm going to do that. So about 15% of the time it's going to pick something else, right? And in case of Epsilon-greedy, it's that probability that's going to kind of go out and look at it. So 1 minus epsilon is going to be your exploitation arm, and epsilon is going to be your exploration arms itself. And this number will remain practically the same, doesn't matter how many steps that we have taken so far. Okay, so that's like your basic concepts around some of the very, very dummy algorithms that are there in multi-arm bandits. Okay, so let's do some hands-on. If you guys want to follow along, happy to follow along. Just type in your comments what would you like to do. If you want to follow along, then I will go step by step. If you just want me to go through the lab, just kind of walk you through that algorithm, I can do that as well. So again, depending on how much time you guys have on your hand, we can play around with that and work through that. Again, up to you guys. The hands-on that we are going to do are going to be on Gitpod. So you know everything is set up. The Docker container is set up. You know, it will take a couple of minutes to set up the whole logic and go from there. So follow along. There are a couple of questions. Let me spend some time to answer them. All right, so looks like most of you are going to follow along. So let's give you the code itself. So here's a GitHub repository, and I'll just show you what we need to do. So if you go on the GitHub repository, there's a Gitpod link. You can just click on that link. I'm assuming all of you have a GitHub account, and you can immediately fire up, or if you want to just spend time to download that, there's a requirement files for you to get started. Alternatively, for people who have used Visual Studio Online and you have an account, you can again get that started as well. For today's example, I'm going to make use of Gitpod so that again all of us can follow along and you don't need any special accounts from there. Now, all of my code is based on a very, very popular multi-arm bandit library that is given by Lilian Besson, or Simpi Bandits. A lot of the code is kind of influenced from there. I've taken that code and kind of simplified it so we can follow along. But over a period of next few sessions, as we go into more and more algorithms, learn more concepts, we'll keep on adding to that code so it doesn't become overwhelming for you and you can follow along and understand, how do you define regret, what are some of the key terms that are sitting in there as well. I'll post the link in the chat so you guys can follow with me on this. All right, so I've posted both the links in the chat, both in YouTube and Twitch. So you can just go on to that. So let me start sharing the code itself. All right, so here's my GitHub repository. Again, I've given you a couple of options. Most of these are just click through. So for Visual Studio Online, if you have an account with Azure, you can just click on it. Everything is all set up. The Docker containers are set up. And if you want to set on Gitpod, that's also easy. Only thing is Gitpod requires you to have a GitHub account, but for now it's practically free. We don't have to do anything else on this as well. So just click on Gitpod and it's going to kind of set up the Docker container. Once you have this set up, just type in your chat that you have you have a working container, and then let's spend some time on the code and working through some very, very basic examples in there, and then get started with the other aspects. When you guys have your code ready and your Docker container is ready, just type in your chat so that I know I can proceed along, because most of you want to follow along. So I'll just wait for a couple of more minutes. All right, so looks like at least a couple of them do have the code ready. So let's move on. So in our multi-arm bandit, right, we have to determine which arm that you are going to pick, right? Now, typically the way you would end up picking the arms is again based on your historical distribution of the data that you have got. You will define those arms as well, right? So I have defined 3 arms in there, where the first arm is a constant reward. So it doesn't matter what you do, it's always going to give you a constant reward of 0.5, right? And you have to define your min and max value. Let me just zoom in a bit so that this becomes easier for you to read. Okay, so the reward is 0.5 at this point, and you can kind of, as you kind of initialize this arm, you can set this up. The other one that we have used is a Gaussian arm, a normal distribution arm, where you can kind of define your mean, which is given by mu, or the sigma, which is my variance. Now I have a default value of variance, but you can override it and set it up as well. right? So for both of these things, right, I have a function which I have defined is the draw function. And the way the draw function works is you have to pick a value from that given arm. So let's say that arm got picked. Now you have to pick a reward that's coming out of it, right? So now you are going to say that, all right, I'm going to pick, so I'm picking a value in here, which is defined by Gauss, which is defined by my mu, which is my mean, and sigma, and I'm going to pick a value out of that, right? Most of these things are just to make sure that I'm picking a value between 0 and 1, and that's the only thing that we have. But my key function over here is just the Gauss given by that. And in constant, if you look at it, I'm just going to return a value of constant reward, right? There is nothing more beyond that. For my uniform, again, I've given, saying that I'm going to pick a lower value and then pick a random value which is based on the amplitude itself. So amplitude is the delta or the difference between my max value and the min value, right? And it is going to give that as my arm. And there are a lot of different arms that you could end up doing. I could also pick a discrete arm. So let's say I have different users with different promotions. I could define a discrete arm where it's randomly picking a reward that's coming out of it. And again, a lot of this is for simulation. Typically, this is a feedback that you would get from the user itself, right? But now we are kind of trying to simulate this environment. That's why we need this arm itself. All right. So in your real life, all you are going to do is have your policies, and these arms become your draw is your real life input that you will get from the environment itself, right? So that's just a distinguishing thing that you need to know of, when you kind of think about putting this into production, how would you end up doing that? Now, my policy itself, I wrote, again, there are a lot of flavors of Epsilon-greedy, and we can kind of do that. So for us, we are just going to pick a very, very simple one that I just explained to you in the presentation itself. Is, I'm going to define an epsilon, right? When I initialize my policy, I set up an epsilon. If you don't define an epsilon, it will take a default value of 0.1. Now, what I say is, with a probability of epsilon value, either it will randomly pick an arm. So if it's within that 10%, right, and I'll show you how I picked it in a moment, it's going to pick a random arm, or it's going to pick the one that has the maximum rewards, right? Similar to what we had said, right? So now it's going to do an exploitation, and with a chance of probability epsilon, it's going to do an exploration itself. So this is very, very simple way of writing these policies out. So that's Epsilon-greedy. And what I've done is to kind of put this in place, I've created an, just a simple environment which allows me to kind of set up the arms and, do a draw, right? So it allows me to kind of pick from the policy itself. It allows me to pick, what I want to draw out as well. And that's all I have at this point, right? So I'm going to return a random sample from the arm, which is drawing T, right? So this is how your arms interact with your policy itself. Any questions on this? Anything that I would have missed or overlooked? Anything you want me to go into the details? So for our examples, the rewards are 0 and 1. And some of these policies do require that your rewards are in 0 and 1. But specifically for our arms itself, your Gaussian arms, you can pick any of your min and max, right? My default is I'm truncating it between 0 and 1, but you could pick a different value altogether, right? But you have to be careful with the policies itself. Is some policies will not like you picking non values that are not between 0 and 1, right? So again, something that you have to keep in mind. Most of the ones that we will use are okay with working that out. But yeah, as you kind of come along, keep that in mind that not all the policies are compatible with any extreme values. So just for sake of example, we will use 0 and 1. All right. If there are no questions, let's start to build our code itself. Now, in the demo.py, which is in the root folder, I have kind of given certain arms in there. And we can work, I mean, feel free to play around with this. Nothing is going to break in there. But let me explain how I did this code. So for my policy itself, I said, pick Epsilon-greedy. I have UCB policy itself, but most likely we'll cover it in our next session. I don't want to rush through things. So in my policy Epsilon-greedy, I need to define how many arms. Most of the policies will require you to let it know how many arms that you are going to do, and pick an epsilon value, right? And feel free to play around with these values. My arm configurations, I have picked 3 arms. All my 3 arms are Gaussians. My means are set to 0.1, 0.5 and 0.9. So very clearly, just out of, without knowing anything, you know that your arm 3 is your best arm. So that's what your algorithm should be picking most of your times itself, right? Now I set up my environment, which is saying that, hey, Mr. Multi-Arm Bandit, set up the environment with these configurations. And I'm going to call it my environment itself. And I've set my horizon to 1000 trials, right? So it's going to run this picking the reward and the options 1000 times. And we are just going to kind of start off with running through this simulation. So the first choice that we are going to do is the policy is going to help me pick the choice itself. Now, if you remember, right, the choices that we had for Epsilon-greedy were going to pick the option with epsilon. So now my rewards are all 0 because there is nothing available yet. So it's going to pick, just randomly a choice, right? So let me close some other windows. All right. The next one is the reward is given by the environment itself, right? So now the environment is telling me is for the choice, give me what is the reward. And this is essentially the choice is the arm that we picked. And now the arm is going back, let's say in the first option that we had is the first arm was picked. Now it's going to randomly pick a value which has a Gaussian distribution with mean of 0.1 and the variance of 0.05, right? So that's where your reward is coming in from. In real life, this is your reward that you would get from your agent itself, right? So now your environment is drawing this choice, which is nothing but going back to the arms, right, and picking the reward from there, right? So let me go back to this code and you can see that this draw function is coming in from the arm. Okay, so that's where the reward is coming. Now the policy needs to make sure that it sees this reward, right? So now I have a get reward function which says that, okay, I made a choice 1 and based on that choice 1, I got a reward of whatever this draw function came out to be. All right, so I have it in my base policy itself so that, I can write a collection of it in there. So now what my get reward does is it increments my time t, right? So I'm going to my next iteration itself. Epsilon-greedy doesn't have anything to do with time, but as we go along, you will see that, time becomes an important factor for the policy to make a decision whether it needs to do a reward it needs to do an exploration or exploitation itself. So now it's going to pick that, okay, how many pulls an arm had, right? So now, I have 3 arms. So, I'm keeping a counter of how many pulls that I did. So I'm kind of giving that choice, which was my arm, a +1. And then I set my reward for that arm, right? So I'm setting up my reward. I scale it back between my lower and amplitude, which is why I said, in this scenario, you can go anything beyond 0 and 1. So your lower and amplitude will take care of scaling the values back to between 0 and 1. And then I set up my rewards for that arm, right? So that's how I go and pick my reward itself, right? And then I store those results, right? And then, later on I want to kind of do this fancy charts and pick these rewards as well, and I keep going back. Now, when I finish these 4 steps, I go back and start all over again with my policy choice, where my policy now makes a choice of, which algorithm it needs to, which arm it needs to pick, right? And let me print some of these values, and let's just do 100 iterations so the values are easier to see. Now again, before we kind of run through this, did you guys get the concepts of, how did we put the arms together? How did we put the policy together and created an environment for simulation? I'll just wait for a couple of minutes to see if there are any questions out there. Let's say the rewards are not, so there's a question on Twitch. Let's say the rewards are not between 0 and 1. There is a change to UCB or Epsilon-greedy? No. Because your rewards essentially get scaled based on the policies itself. So for example, let me go back to my base policy. So over here, based on my lower and amplitude, my rewards get scaled back to 0 and 1. And that's something that you have to keep in mind, right? Make sure that your reward is kind of making that choice, and your values are not skewing your rewards itself. So that's where my base policy will kind of come into there. UCB is just going to pick the rewards and define the pulls. Again, I don't want to go into the details, but because your rewards are automatically scaled between 0 and 1, there is no further changes that we have to make in here. Alright, so now let's play around with the demo. We'll start off with Epsilon-greedy, and I'm going to hit the run button. Most likely it's hidden behind my video, but you can see the green triangle on the top right. Just hit the run, and it's going to kind of just run this in an environment, and you can see that for most part it has picked 1, right? That's where your rewards are. Which is not right, because 1, just knowing from the configuration itself, is that it's a bad choice, because 1 is giving you a bad reward, while your actual better rewards are for the third arm, which should be given by index 2. So let's try to run this again for maybe a longer time, and see if any of these answer changes, right? I'm just going to remove these options in here, so that we can see just by counter which one gets picked up. All right, so again, because it picked 1 as the first option, it's very difficult for Epsilon-greedy to move to an optimal arm, right? Even if I run this for 10,000 runs, let me just clear this. You won't see that it will easily move into an optimal arm itself, right? It typically sticks with that first choice that it made, and that's what it kind of continues to do, right? 10% of the time it ended up going and doing something else, but for most part it was getting stuck with the suboptimal choice that was what it ended up picking. So of course this is not a good choice that we have. So just for, we'll not get into the details of this algorithm. What we will do here is, instead of epsilon-greedy, I'm just going to pick UCB, and UCB doesn't have the value epsilon, so I'm just going to remove it and see if my answer changes drastically based on the choice of algorithms itself. Right? So now you did see that very quickly it moved on to my better arm, which was arm number 2. And you can see that for most part it's picking arm 2. Let's lower down the number of iterations and see if the result is consistent with what we have set up as well. Yep, you can see that very quickly it found out that arm 2 was giving better rewards, and we will end up picking rewards as well. So these are some of the intelligent ways in which very, very simple concepts can build on the knowledge base that you have, and you can start driving better algorithms in there. And what we will do in the next streams is that we will spend some time, more time on the algorithms itself, play around with these concepts, build some charts and everything, so that you can play around with these concepts. Again, I'll let you guys play around for 5-10 minutes, see again if there are any questions that you guys might have, which I could answer before we close the stream itself. Yes, so there was a note from one of the users, Vidya Raman. So if I increase my epsilon in epsilon-greedy, arm2 getting picked up, right? So that's where you kind of do the trade-off. and you do find out that now you have to do more exploration before a better arm gets picked, right? So that becomes your kind of suboptimal. And one exercise that I would probably ask you to do is for the same number of runs, and we'll kind of cover those ideas in the next topics as well, of how do you define regret, right? But for the same number of arms, run UCB and run Epsilon-greedy, and just take a look at how many times do you get the arm 2 getting picked up, right? Does Epsilon-greedy gives you more regret, which means that more times it picked some other arm as compared to UCB. So let me run that piece. So let's do UCB in here with let's do 1000 results, and let me run it. Right, so I got my values. Let me just paste it here so that we don't forget it. This was UCB. Now we have Epsilon-greedy with 3 arms and value of epsilon to be 0.02. All right, and let's keep the same horizon, and let's run it and see what we get. So you will notice that in Epsilon-greedy, I got, my arm 2 was picked 877 times, and your total regret was around, regret is, in this scenario, how many times it picked a suboptimal arm. Now in real life, there's no way to kind of compute some of these things because you don't know what could have been the reward. But you can see that, in Epsilon-greedy, about 123 times, arm 1 and arm 0, or the first arm and the second arm, were picked, and you got a option over there. While in your UCB, you just got about 67 arms, so probably just about half of it. So in UCB, of course, the algorithm is kind of picking a better arm very quickly, and that's what you want to kind of get at, right? You don't want to kind of lose out on exploration while at the same time compromising on your exploitation itself. So that's a trade-off that a lot of these algorithms come up with, and some of these algorithms go very, very complex, and we will learn to do more. But you can now immediately see the difference between UCB and Epsilon-greedy. Again, don't worry about the logic itself. In the next session, we will go deeper into that and then build on the concepts on top of that. And right now we just did this one repeat. Typically when you are kind of doing this as simulation for your practical examples itself, you will do the simulation a number of times, right? So you will run this 1000 iterations or 10,000 iterations, probably 1000 times or 10,000 times. The only reason is, a lot of this is random numbers and random choices, and something that you don't want, that you made a bad choice because you had a random number that was picked that was not optimal. So to kind of eliminate that, you do this Monte Carlo simulation where you will run these steps, which I have, right? This 1000 iterations that I'm running, probably 1000 times, 10,000 times, and then you will take average of that reward to see how that works. Right now, for time constraints, we are not going to kind of look at it, but this will give you a very, very good way to understand how we kind of do that. Again, we'll build out on those concepts as we build more complex ideas, but that's a starting point for you guys to play around with and understand, how multi-arm bandit works. All right, so I think that's all we have for today. I have just a few more things to share with you guys. Okay, so today we kind of looked at, just the basic fundamentals of multi-arm bandits, how they work, basic policies, on Epsilon-greedies, and again you played around with the code itself. So something that we'll continue as well. Next week I wanted to kind of play around with more algorithms, and maybe we do a longer session. Again, if you guys are interested, we could cover more, but there are a lot of flavors of UCB, and I will kind of link those papers and everything during the sessions itself, but something that you could look at going in. There are some not so well known things itself for BESA. Again, there are quite a few of them. We could look at that, and going in again we could look at more algorithms, or more applications, or even move on to more of contextual bandits. Is how do you kind of make some knowledge about the user or the state that they are in, and make an intelligent choice going on top of that. So just drop in your code note itself of, hey, how we can kind of work that out, and what would you like to see more. All right, so there's a question on YouTube. Is reinforcement learning used in stock markets to find the best time to buy or sell? I'm not sure. And if people are using it, of course, it's not in public domain. But again, not heard of any practical examples for obvious reasons. Because if somebody knows that how to exploit reinforcement learning, they would, of course, go out and use it. I know a few startups in Singapore that are making use of reinforcement learning to do exactly that. But what policies are they using, how they are kind of working through, is probably beyond my scope of it, right? I come in from a very internet product savvy kind of org, and that's where my mindset is. So those are the things that I can associate it with. Probably not so much in finance, which some of you have kind of asked that before, both on Twitch and YouTube. Again, let me know in your comments if you guys are okay with this. We can spend some more time on algorithms. We can keep adding and expanding our library so that you guys build more confidence in using multi-arm bandits and use them in your day-to-day applications as you go along. All right, so I will see you next week. Do subscribe on Twitch or YouTube. Because typically every time I try to schedule a session, it usually doesn't end up working that well. So do subscribe. So, as soon as we go live, you will get an alert, and that's the best way to kind of look at it. I would do appreciate if you're on YouTube, hit a like button on the session. It's really motivating. But having said that, right, if there are any comments, anything you would like to go deeper, again, let me know in the comments itself, and we can spend some more time on doing that. Next week is going to be algorithm week. We will spend some time on some key concepts, again, building some intuition in there, and work out from that point onwards.